if error occurs, if that is a data transmission from one place to another place, then it is relatively easy to fix the error by asking the sender to retransmit the data. But however, within the computer system, especially between memory and some other place like a CPU, but this cannot be done. And too often, the copy of the data is important. And then if a reader fails, and asking to send again is not very practical solution. Thus, to provide the data integrity over long-term error correcting codes are required. At least error detection is very important within computing system. So to do error detection and correction, there are many theories there, and one of the most popular ones are Hamming codes and the Reed-Solomon codes. The Reed-Solomon codes are particularly useful in correcting burst errors like a CD-ROM. When you got a scratch on the CD-ROM surface, then the block of data got error, so it's a kind of a burst error. So Reed-Solomon error correction algorithm is best for that. But the Hamming codes are very simple compared to Reed-Solomon. So in this class, we will just learn simple ones, Hamming codes in detail. So by definition, Hamming codes are code words. Here, code words means a bit pattern. If you have 8-bit, you have 1010 and so on. So those bit pattern is code words. So code words are formed by adding redundant check bits. Here, redundant means in addition to the original information. Suppose we have 4 bits information, then Hamming code is add some more bits, which is not part of the information, but add some redundant bits, and then to make the data word like that, so that using those redundant bits added by a certain manner, we can detect or correct error. In this development, we have a terminology that's called Hamming distance. Hamming distance between two codes is the number of bits in which two codes are different. So for example, we have 2 code words in 8 bits. Then the number of bits are different between the two is here, here, and here. So 3 bits are different. So we say it's a Hamming distance of 3. So in general, the minimum Hamming distance means given code between all possible pairs of code patterns, what is the minimum, smallest distance you get? Suppose we have 3 bits. Then you can have 8 different code words by having 0, 0, 0, and 1, 1, 1, that to pick up any possible 2 combinations of words, a pair of words, and then check Hamming distance of each pair, and the smallest number is called the minimum Hamming distance of a 3-bit code word and the like. So the first, let's find out how to detect error. Detecting error is much simpler than correcting error. So detecting error is as follows. So minimum Hamming distance for a code, let's have a notation d min, determines its error and then correcting capability. So let's focus on detecting error first. To detect the k or less than k single bit errors, the code must have a Hamming distance of minimum Hamming distance of k plus 2. So that here, if you want to detect 1 single bit error in the code, then minimum Hamming distance should be 2, which means all possible pair of codes. Just check the Hamming distance. Then the smallest should be 2. Then we can detect a 1-bit error. So let's see what does this mean. Suppose we have a 3-bit data, and then we use all possible bit combinations, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 110, 111. So if you use all 8 possible bit patterns as a data, then we cannot detect any single bit error because Hamming distance of any pair of code word, suppose those two Hamming distance is 1, those two Hamming distance is also 1, those two Hamming distance 2, and so on. So smallest Hamming distance is 1. With the 1, you cannot detect what you can detect is 0-bit error. The reason is quite obvious. If in any of the code words, suppose let's pick up this one, if any single bit error occurs like this, then that becomes one of the valid code word in this 8-bit information. So we are unable to detect any error in this case. So to detect one single bit, there should be minimum Hamming distance should be 2, not 1 like that. So which means we cannot have a 3-bit to detect error. We need to add more bits appropriately so that we can detect one single bit error. So simplest means of detecting one single bit is have a parity bit. Add 1 bit as a parity, and that bit determine the value as follows. If you want to use an even parity bit system, then the whole information, the number of ones should be even. So you add one additional bit called parity to enforce this condition, that is a number of ones should be even. Suppose we use 8-bit information, then we add one more bit as a parity bit here, there. Then what should be the value of this parity is depending on which parity system you are going to use. If you are going to use an even parity, then number of ones should be even, so we have 4 ones, so parity should be 0. But if you're on an odd parity system, since we have 4 bits, the value should be 1. So that number of ones becomes odd. So you add one more bit in that way, so based on even parity or odd parity. Then suppose we are using other parity systems, so we have added 1 here. Suppose that one single bit error occurred, so like here it becomes 1. Then we find that since the number of ones is 1, 2, 3, 4, 5, 6, so it's not even, not odd, so this is not valid data. So we can detect one single bit error. Of course, if 2 bits of error occurs simultaneously, those 2 becomes 1, then number of 1 is odd, so we are unable to detect the error. So here, by adding one more bit as a parity, all we can do is detecting one single bit error. That is this formula. To detect k single bit errors, Hamming distance should be k plus 1. So in parity system, 1-bit parity system is Hamming distance is only 2, so you can detect only one single bit error.